Hello, my name is Houssam Houssein. I work in Aircom company and also in LGLL laboratory. I will present to you my work about the development of an algorithm to treat mechanical contact between bodies using FreeFEM. And this algorithm must be symmetric. I will explain later what I mean by symmetric. First, let's start with some basics and some notations. We will take a body omega in its initial configuration. And if we apply a load on omega, it will become phi omega. Phi will describe this transformation. And if we take a material point big X, it will become small x. And small x will denote in the following the actual position of the material point big X. And our displacement field, which will be our unknown, and the following will be small x minus big X. We have two kinds of problem. First, we have the linear elasticity where we have small deformations and we don't distinguish between the initial configuration omega and the actual configuration phi omega. And we have finite deformations where we have to distinguish between omega and phi omega. In addition to the balance equations, for example, here sigma will denote the Cauchy stress tensor, and pi and p is first pure Kirchhoff stress. We have boundary conditions. For example, here at gamma 0, we can impose a displacement, and in gamma 1, we can apply a surface load. Our displacement field is also a solution of the minimization problem of the total potential energy E over the admissible set V, where here we impose a directly condition on gamma 0. For example, in the case of linear elasticity problems, we have a constitutive law in order to describe the behavior of the material, for example, Hooke's law. And also our total potential energy can be written in this form, 1/2 AVV minus FV, where A is a bilinear application, continuous and coercive, and F is linear and continuous. And we can prove here the existence and the uniqueness of the solution. In the case of finite deformation, and more specifically for hyperelastic materials, our total potential energy can be defined by the integral over omega, the initial configuration of a strain energy function psi minus Fv, the potential energy of the forces. And with some properties on psi, for example, polyconvexity, Jean-Paul proved the existence of a solution of this kind of problem, the minimization of the energy over the admissible set V. Now, the Signorin's contact problem is a contact between a body and a rigid foundation. It's a nonlinear problem, and we don't know actually the real contact area. But we suppose that this real contact area is included in phi gamma c. Phi is the transformation, and gamma c is a potential contact area in the initial configuration. The displacement field is a solution of the minimization problem of the energy E, the potential energy E, over the set K, where K will describe the non-penetration between the body and the rigid foundation. For example, an example for a non-penetration condition, for example, for each X, the actual position on phi gamma C, if we take its projection on the rigid foundation Y, X minus Y scalar the normal vector N will be always greater or equal 0. For example, at the real contact area, this quantity is equal 0 because X and its projection is the same. And where we don't have contact, for example, here, this quantity is strictly positive. For example, in the case of linear elasticity, our problem also can be written in the form of a variational inequality and using properties on A and F. And because K in this case is convex and closed, we have a uniqueness, we have a solution which is unique. Also, we can use some arguments and we study the energy in order to prove the uniqueness of the solution. Now, the contact between two bodies. Here we have two bodies, omega 1 and omega 2. Our unknown is the displacement field of these two bodies and is also a solution of the minimization of the potential energy of the first and the second body with some non-penetration condition. For example, here we will take the first body as a slave and the second one as a master. What I mean by slave and master? It means that our non-penetration condition will be written in this form for each x1 and the contact potential area of the first body. If we have its projection, the non-penetration in this case will be x1 minus x bar. Scalar, the normal vector n will be always greater or equal 0. For example, if we take the second one is a slave and the first one is a master, x1 will be on this area. And if we take the second one as the slave and the first one as a master, we will not obtain the same solution if we take the first one as a slave and the second one as the master, especially when if we use the finite element method. Therefore, this formulation is non-symmetric, and the user must choose between the slave and the master body. For example, we have different ways in order to help the user to define the best slave. For example, if the first body has the finest mesh or is less stiffer than the second, therefore we can choose this body as a slave. But what if this body has the finest mesh and is more stiffer than the second body? Therefore, we see the difficulty to choose between the slave and the master. Also, this issue occurs if we have a contact between more than two bodies or in the case of self-contact. Hence, the need to create a symmetric algorithm or a symmetric formulation in order to treat this issue and also in order to not distinguish anymore between slave and master body. First, we have several methods. I will start with the penalty method. The penalty method will transform our constrained minimization problem into unconstrained one. For example, here in the case of linear elasticity, in the case of Signorini's problem, just to be more simple, we minimize our energy here, our potential energy here, plus a penalty factor mu, which must to be very big, multiplied by a penalty functional. The penalty functional, when we have a penetration between the two body or the body and the foundation, this penalty functional will be strictly positive, and if we don't have a penetration, this quantity will be equal to 0. For example, here we have an expression of the penalty functional. It's integral over gamma c. Gamma c is potential contact area and the initial configuration of a eta function applied at the non-penetration function. This quantity here must be always greater or equal 0. And we have also some properties on eta. I won't go into details. Now we will apply our penalty method in order to make our algorithm or our formulation symmetric. First, we will take the first body as a slave and the second one as a master. And we will write our non-penetration condition. And after, we will take the second body as a slave and the first one as a master, and we will write our additional non-penetration condition. And we will use our penalty functional P1 in order to penalize the penetration when we consider the first body as a slave and the second one as a master, and the penalty P2 in order to penalize the penetration when we consider the second body as a slave and the first one as a master. And we will obtain at the end our symmetric formulation. It's a minimization of the potential energy EP plus a penalty factor mu multiplied by the two penalty function P1 and P2. And here, because if we don't have a penetration, our penalty functional are 0. And our algorithm, we impose a lower bound for the displacement. Now we have another method For example, here we consider at first the first one, the first body as a slave and the second one as the master. And we have this non-penetration condition. And instead of using this non-penetration condition for each point at the contact area of the first body, we will use a weak form of this non-penetration condition. For example, here, our problem will be a minimization of the energy, of the potential energy, with NC1 inequality constraints. Here, NC1 is a node number of gamma C1. And the phi I is a shape function at each node of the contact area gamma C1. Of course, this formulation is not symmetric, but if we simply just write the symmetric problem by adding and by considering in addition that the second one is the slave and the first one is the master, we'll obtain a minimization problem with NC1 plus NC2 inequality constraints. And here NC2 is the number of nodes at gamma C2. For example, if we use an active set strategy or status methods, for example, if we compute the Jacobian of this inequality constraints, we may have numerical difficulties. Why? Because we may have in the Jacobian of these constraints row vectors that are linearly dependent. And therefore, if we use the Newton methods, we will obtain a singular matrix and we'll have a numerical issue. In order to avoid this problem, we'll use the interior point method. Yeah, this method is close to, with this weak formulation, is close to Morton method. And our problem will be written in its general form as a minimization of the energy E. U here belongs to Rn. U, it's the degrees of freedom of the displacement field because we use the finite element method. And here Cu will be the non-penetration condition. And here the inequality between two vectors are the inequality between each components of each vector. And we will use the slack variables, which are an artificial variables, in order to transform our inequality into a equality constraints with S is the slack variables. And here we will obtain this problem. We have equality constraints here, and S will be greater or equal to 0. Here, all our constraints are linear, therefore are qualified to the KKT condition. And here we have another formulation. For example, here, if we don't want to if we don't want to this inequality constraint to be activated, we can, for example, penalize the slack variables to be negative. Here we use a method of penalty in order to penalize the slack variables here Si to be negative, and we impose a lower bound here with a negative value. And here this inequality will never be activated. And this formulation we obtain the same results, and we don't obtain a numerical difficulty using these two formulations. And here is the penalty factor, because this penalty function eta have some properties, we can take as big as we want, in fact. And after, because here we will transform our problem here into a barrier problem in order to take into account this inequality. And after, we will obtain a minimization of a barrier functional with just equality constraints. Here, I will not go into details, but after we will use a descent method plus a line search method in order to solve our problem. And we will apply a Newton method to find the descent direction. And in our linear system, we will obtain a matrix of this form, where A is the Jacobian of the equality constraints and is a full row rank because we introduce the slack variables. And here, for example, in the case of linear elasticity, this matrix J is positively defined in the null space of the kernel of A, the null space of A, and therefore it will not be singular. Here I will briefly describe our algorithm. Here we will use the fixed point algorithm in order to transform our problem or contact problem into a sequence of problems with linear constraints. For example, we can see this strategy also used in Codaster. And it's used also more specifically for the large deformations because for linear elasticity by but theoretically we have a linear constraints for linear elasticity, and therefore we will because in our formulation we have integrals, therefore we will use we'll proceed by choosing the integration points. For example, here we will use the previous iterations in order to find for each integration point xs at the contact area of the first body. We will find the closest segment to this point, and also we will compute the projection, the position of its projection x bar in this segment, and we will use this position of x bar in the actual iteration n. And therefore, for the actual iteration, we have the non-penetration condition will be xs minus x bar, scalar the vector n will be always greater or equal 0. And x bar, because we compute its position from the previous iteration, will depend linearly on the degrees of freedom of the second body, and xx depends linearly on the degrees of freedom of the first body. Therefore, we have linear constraints at each iteration. And we can use the penalty method or the interior point method in order to compute our displacement field. And in this case, our displacement field is the degrees of freedom of this displacement field, because we use the finite element method. And this algorithm converges when the error between two successive displacement is small enough. Otherwise, in the case of Signorin's contact problem, the contact between a body and a rigid foundation, and if our rigid foundation can be described by a C2 function, or for example, we can use cubic spline. Therefore, we have a very simple algorithm in order to treat this contact that doesn't use this fixed point algorithm. You can see it in the reference file. Now I will present some numerical validations using FreeFEM, also using IP-opt in order to solve our optimization problem. Here we have two elastic blocks. I impose a downward displacement at the top of the first body in order to make contact between the two bodies. And the goal of this test is to ensure that the pressure is transferred to the second body through the contact area when we have no conforming meshes between the two bodies. And we don't see an horizontal deformations because here the portion ratios are equal to 0. And here on the next figure we can find a constant pressure at the contact area. Now we have a quasi-static study. Here we are in the case of large deformations or finite deformations, and here we have two Neo-Hookean materials. I impose at the first step a downward displacement at the first body, and after at the second step I impose an horizontal displacement. As we can see in this video, the color is just for the displacement, and this small body is 10 times more stiffer than the second. Yes, and here also we are in the case of finite deformations, and we have two Neo-Hookean materials. The bigger disk, the outer border of the bigger disk is fixed, and we impose a vertical displacement at all the nodes of the smaller disk, and it's also a quasi-static study. Here we have some papers. For example, if you are interested in a very simple algorithm to treat Newness problem, you can see this article. It's a very simple algorithm, in fact. And thank you. And before that, I will show you just a small video about a dynamic case in this case. And here we threw two balls. The first one is less heavier than the second, and we threw these two balls on a rigid foundation. Yes, and we threw it with the same velocity, and we see the bouncing here. That's all, and thank you.
So thank you, Houssam Houssein, for this presentation. You have time for one question or more.
Sam, did you parallelize your code?
No, we parallelized the one. We did a formulation with Newness problem, but it's very different than these formulations. We parallelized with Pierre Jolivet this formulation, but here no, it's not parallelized. But for example, for the Newness problem, where just we have a contact between a body and a rigid foundation, I think it's very simple if we use tau for doing minimization. But in case of contact between two bodies, I don't have any idea how to parallelize it. For example, especially for the domain decomposition, I will see with Pierre how to do that.
Okay.
Okay, so thanks again, Houssam.
Sorry. Your condition seems to be based on discrete sense, or several IPI.
Here, yes.
In the continuous case, continuous formulation.
In fact, here, yes, it's based on the discrete case. Yes.
But on the at the very beginning, it could be possible to write by continuous case, and then after that, we can introduce kind of the mortal technique or something.
I didn't hear you very.
It's possible to write in continuous case, and then after we can introduce another discretization to satisfy solvability, like mortal.
Okay, but it's. Yes, but this formulation, it's more like mortars, in fact, and also the same. But because I'm interested in the discretized formulation, I don't see why I do it in the continuous formulation. In fact,
because I'm a bit curious about the solvability of the matrix.
But excuse me.
So of the matrix could be singular if the number of node is not compatible.
Yes.
So if we introduce a continuous case and then put good discretization, that problem never not be happen. That is my question.
Continuous case, and I don't know if we put a discretization. I don't know, but because here the singularity, it's more specifically if these two vectors are linearly dependent, in fact. And here, for example, in this case, we will not obtain, or when we introduce the slack variables, we will not obtain a singular matrix, but just I don't know. In fact, I don't know.
Yeah, thank you. Maybe we can talk later. Thank you.
Yes, we can talk. Yeah.
Okay, so.